and the carbonyl is the perfect candidate for that. So why not just add another carbonyl directly adjacent, and let's see what that can do. At the beta position, let's put another carbonyl. Let's put a hydrogen here. So this lone pair with the negative charge can travel towards the right and form a pi bond right here, and what that will do is send up the negative charge to this carbonyl oxygen. On top of that, it can travel towards the left and send an electron pair up to this carbonyl, which would then bear the negative charge. So if we draw out the resonance structures for this compound here, what we'll see is that one contributor will have the negative charge at the alpha position, another one with the negative charge here, and another one here. Basically what we've done is disperse this negative charge over 5 atoms, and we don't have any electron donation from these hydrogens. So that means the pKa of this compound is really low. It turns out it's close to 6. What we're basically doing is sandwiching the lone pair between 2 electron withdrawing groups, which enhances the acidity dramatically. Now it also follows that if you put alkyl groups that flank this compound, the pKa would rise because alkyl groups are electron donating. It also means that if we put 2 ester groups here, for example, this is a dimethyl ester where you have a methoxy group here and a methoxy group here, well, those groups are electron donating by resonance, because on top of sandwiching it between 2 carbonyls, we're also introducing 2 competing groups by resonance. And we see that here in diethyl malonate, which looks like this. And we're imagining we formed the enolate at this alpha position, so let's put in that lone pair. So let's analyze diethyl malonate just like we did with this compound. We have 2 electron withdrawing groups in the form of carbonyls, but we also have 2 electron donating groups here. So if we use the pKa of 6 as the baseline, introducing this diethyl ester portion means the pKa almost doubles. It's actually close to 13. So let's see if we can rank the compounds based on acidity, based on what we discussed. And we need to rank in terms of decreasing acidity. So let's find the most acidic compound first. So the first thing to do is draw in all of the alpha positions, which can be deprotonated to form the enolate. And now let's go step by step. This structure is acetoacetic ester, and we understand that there is an alpha carbon here, but the issue is that one isn't sandwiched between electron withdrawing groups, which means these alpha protons won't be as acidic as these alpha protons at this position. So what we have are 2 electron withdrawing groups and 1 electron donating group, all of which are by resonance. Now in 3-pentanone we have methyl groups that are flanking both of the alpha positions. In terms of nucleophilic attack on the carbonyl carbon, the reactivity is really attenuated, it's really reduced. But if we look at just the alpha acidity, that's also reduced. We just have electron donating groups by the inductive effect. So roughly the acidity of these alpha protons is close to about 20, close to acetone. Compound 3 is similar to compound 1, where we've sandwiched one of the alpha carbons between 2 electron withdrawing groups. We don't necessarily have any electron donating groups aside from this methyl group. So technically, if we go back to acetoacetic ester, this methyl group is also electron donating to some extent, but not by resonance. Now let's look at compound 4, ethyl acetate. This is our alpha position. We do have an electron withdrawing group, but also an electron donating group by resonance. So it doesn't seem like this would be very acidic at all. Probably the pKa would be close to 24 or 25. Finally, let's look at compound 5. So what we see is a pattern where we can compare compound 5, 3, and 1. Because in all cases we've sandwiched that alpha position between the 2 carbonyls that flank it. What we then do is compare the side chains and rank it based on acidity there. Now let's review. Acetoacetic ester has 2 electron withdrawing groups and 2 electron donating groups. This one by hyperconjugation. We could also say the inductive effect, but this one by resonance. In 3-pentanone, we do have this electron withdrawing group, this carbonyl, But then we also have two methyl groups that are flanking both of our alpha positions. But if we focus on just one alpha carbon, let's say it's just one electron donating group. In compound 3, we have two electron withdrawing groups that can delocalize the negative charge at the alpha position if we form the enolate. We don't have any group towards the right, but towards the left we have a donating group in the form of an alkyl group, the methyl. Compound 4, ethyl acetate, has one electron withdrawing group, the carbonyl, and the ethoxy portion, the donating group, which is by resonance. And lastly here, compound 5 is just like 3, except now we have the extra methyl. So 2 electron donating groups compared to 1. Now what's the point of doing this analysis? What we want to do is increase electron withdrawal and decrease electron donation. And we want to do that because the aim is to find the most acidic alpha proton, basically the most acidic compound. So let's compare 1, 3, and 5, because those are the ones with 2 withdrawing groups. Well, it turns out compound 3 is most acidic, because on top of having 2 carbonyls, we just have 1 electron donating group here. Whereas in 1, we have 2, 1 by resonance, and here we also have 2, but not by resonance. So compound 3 is most acidic. So let's eliminate choice D and E. Now comes compound 5 versus 1. The only difference here is that we have the ethoxy portion as the donator compared to the methyl, which is also an electron donator. Now resonance has a more powerful effect in terms of electron donation, because here we have 2 lone pairs, any one of which can establish a pi bond in a resonance contributor. So overall what we see is a partial pi bond character between the carbonyl carbon and this ethoxy oxygen, which means its electron donating capability trumps that of a methyl. So we say compound 5 is more acidic than compound 1. And from all of our choices, choice A would be the only answer, where compound 5 is more acidic than compound 1. Let's just make sure that ranking system makes sense. 3 is most acidic, 5 is then the next one, followed by 1. And if we compare the symmetrical ketone versus ethyl acetate and ester, it follows that 2 is more acidic than 4.